In this presentation, I'll be providing an overview of computational linguistic concepts. Specifically, we'll discuss the kinds of linguistic knowledge you'll need in order to accurately query text data using PDL and XPDL. So first, let's think about how we, as humans, understand language, because there's a lot that goes into reading comprehension. Many of us don't think about all the steps involved when we're doing this day to day, but what if you had to describe this process so that a computer could learn to comprehend our language? So to do this, let's start with an example and go through the steps of how we understand language as humans. Then we can extend that to how we can make machines understand language in a similar way. Let's start with a language most of us don't know and talk about what information we need to understand it. So here's a sentence in Malayalam, a language spoken in South India. What will we need to have to be able to understand this sentence? What's our first barrier to comprehension? Well, our first problem is that we don't know what the words are. This means we need a Malayalam lexicon, or in other words, a mental dictionary that contains all the words in this language. So, none of these three words appear in the lexicon or dictionary, at least not in their current forms. But let's look at the components of these words a bit more closely. Now, what if I told you that the parts marked in blue are common suffixes? So this explains why we might not find these words directly in our Malayalam dictionary, because it's the black portions of these words that would be listed. So our dictionary would list the meaning of these words for us, which I'll disambiguate for you now into their English equivalents. We see that the first Malayalam word translates to kid, the second one as civet, and the third one as follow, plus some suffixes. So the next question you should have is, what is the meaning of those suffixes or endings? This means we need information about the morphology of the language, or how words are structured internally. This includes suffixes, prefixes, or any way you can change words to add information to them, like making cat into the plural cats, or play into the past tense, played. So in Malayalam, the first suffix here turns kid into kids, just like we have the suffix s in English. The second is an object marker, to tell us that this word is the object of a sentence. And the third tells us that the verb form here is following instead of followed or follows. Now that we have the words, the next question should be whether we know what all the words mean. We probably all understand kid and follow, but what about civet? This is where semantics comes in. It basically encompasses what it all means together. So we see on the left that semantics interfaces with the lexicon and morphology. This is because words have meaning and the morphology, or word transformations, also have meaning. Now to answer the civet question, a civet is this small mammal in the mongoose family here. So the last thing we need to understand for this sentence is the word order, or syntax, which is essentially how the words are put together in a sentence and how that signifies their relationship with each other. Now, in Malayalam, sentences follow a subject-object-verb pattern. So in our example, kids is the subject, civet is the object, and following is the verb. In English, we follow a subject-verb-object pattern, so we'd say the kids are following the civet. So these are the four areas of linguistic knowledge needed to understand written text. And your brain is actually processing all this information whenever you read or hear something. We never think about it because it happens so fast. Now, let's step through these four linguistic areas from a computer's perspective to see how a good text analysis system can mimic the very human task of reading for comprehension. We're going to start with lexicon. Remember, that's the dictionary of all available words and what they look like. So let's say we have a sentence like this. The physician had a patient who was infused with Lemtrada in August and is experiencing persistent muscle pain. Now remember that in all of this, the computer is just reading symbols, so the first step is to tell it how to identify words. We do this by a process called tokenization, where individual words, phrases, punctuation marks, and other symbols are split up and stored in a structured form for further analysis. All further text analysis techniques are based on these tokens. Tokenization is fairly straightforward in English. We basically just split them along the spaces. However, in languages like Chinese, tokenization is a much more challenging task. This is because in Chinese, the words are not split with spaces, and context is needed to distinguish where the word breaks are. And even in English, where tokenization is generally straightforward, there are a few exceptions. For example, contractions like the word haven't need to be split up, but idioms should not be split up into their individual words. So, for example, the idiom jump the gun only makes sense as a single phrase. Because each language has its own unique challenges, it's important that we take all their linguistic features into account. And in PolyAnalyst, we now support these features in 16 major world languages. But for now, let's get back to talking about other lexical tasks as they relate to English. For example, sentence splitting. Now, sentence splitting itself isn't a lexical task, but we need lexical information to do it properly. So in English, we do a basic split along the periods, question marks, and exclamation points. Of course, there are some periods that don't indicate a sentence boundary. For example, the period in the abbreviation for doctor, or email addresses that use periods to designate spaces between the words, or numbers that contain decimal points. So we need to take these exceptions into account. But in my opinion, the most important lexical task is to take each of the words identified in tokenization and tag it with its part of speech label. So things like noun, verb, and so on. Now this might seem basic because our brains do it automatically, but to a computer, the noun patient looks the same as the adjective patient. So deciding which one it is not as simple as our brains make it out to be. A system like PolyAnalyst performs this task by using a machine learning algorithm that's based on statistical frequencies of each part of speech label, as well as the word's context. Then it supplements the algorithm with some rule-based tagging to improve the accuracy. And just as clean data is the foundation for everything that follows, accurate part of speech tagging is vital for morphological and syntactic analysis, which we'll be discussing next. So now that we've taken care of the lexicon, let's talk about morphology, which is the internal structure of the words. This includes things like suffixes, prefixes, and any other ways you change words to add information to them. Now, when you search for the word infused, you want to capture all of its forms, correct? So in addition to infused, you also want to capture infuses, is infusing, and infuse. Now, the word confused looks very similar to infused, and we know it's not another form of the same word entry in a lexicon, but a computer doesn't natively understand which differences are meaningful and which ones aren't. So each of these words here are different forms of the verb infuse. In other words, infuse is the lemma, or the main form of the word that you'd find listed as the head entry in a dictionary. And the process of grouping these different word forms together and identifying the underlying lemma is called lemmatization. So when a computer tries to lemmatize words, it uses stemming algorithms. So stemming algorithms try to break down the words into their component parts. like removing the past tense ed ending in English. But we may also need lexical information to do it correctly. So, for example, irregular forms like go and went, they don't have any real surface similarity. So we'd need morphology dictionaries to lemmatize those properly. Also, the verb filling and the noun filling look identical to a computer, but they have different lemmas, so they're different words. And information about their part of speech tag helps a computer differentiate between the two. Now, both lexical and morphological information are needed for a computer to do basic text analysis tasks, like counting words and extracting information based on lemmas. These are also the basis for some of the other analytical tasks we'll need to perform. So at this point, I'll talk a little about indexing so that we understand why it's helpful to reindex after any change in the text when working on a project. So essentially, indexing is the process of internally listing words in their positions. So just as an index in a reference book can help you find things faster, indexing our text helps software find things faster when we make queries. Let's take a look at an example. We have the sentence, "Kids love candy." So for this sentence, the first character is position 0, and that's where the word kids can be found. And our next word, love, starts at position 5. So instead of having to read each document again for every search, the computer can simply search over the list of lemmatized and part of speech tagged words based on these positions. Now, there are different types of indexes. The forward index sorts by position, and this type tends to be very slow for the system to search. So text mining tools like PolyAnalyst use what we call an inverted index. In the inverted index, the tokens are sorted alphabetically by lemma instead of by position. The drawback is that it takes more processing time to create the index, but it greatly increases search speeds for downstream tasks that reference it. So to come back to our previous example sentence, we can see that the word was, its position and other information, is saved as part of the lemma for the word be. And the same happens for the word is. This is why we should always index again after making changes in the text, such as if we are replacing terms or spell checking, because these types of things make changes to the position and associated information of the words. So, by running a new index node, the software can quickly access that information for later processes. Now, let's move on to semantics, which refers to the meaning and the relationships between words with similar meaning. So, let's continue with the same example. Now, we know patient is a person, and Lemtrada is a drug, and muscle is a part of the body, and pain is a bad thing, and a possible side effect. So, advanced text analysis systems like PolyAnalyst can apply knowledge systems or ontologies that are in the form of structured dictionaries. And these dictionaries contain this sort of semantic knowledge and word relationships. So this allows the computer to draw similarities between non-identical records. So for example, the words persistent, constant, and ongoing would be considered similar types of muscle pain because they're synonyms. So with semantic dictionaries, we can tell the computer which differences are meaningful and which ones aren't. So this here is an actual medical ontology entry. As you can see, it has an extensive list of hyponyms. Now, hyponyms are words that are members of a broader category. So, for example, thyroid dysgenesis belongs to the broader category of thyroid disease. Now, a simple search for all instances of thyroid disease, that won't return all of these because they don't specifically say thyroid disease. But if we search for hyponyms of thyroid disease instead, we'll be able to find them without searching for each type of thyroid disease individually. We could also show other types of relationships, like meronyms, or parts of things, like gaskets and pistons are part of an engine, which is part of a car. We can also define word classes, which are lists of words with similar semantic and syntactic function. Now, these would occupy the same place in a search pattern, and even though they're not exact synonyms, they're close enough for the questions we're trying to answer. So, for example, we can add a word class that includes these words here, infuse, inject, administer, dispense, which all have the general meaning of delivering some substance. Word classes are customizable to your dataset or domain, so you can use them to generalize patterns with certain sets of words that aren't technically synonyms of each other. And this is particularly useful for sentiment analysis. So we know, for example, that pain is a bad thing. So if it's mentioned, the patient probably had a negative experience with that drug. One more thing related to semantics is negation detection, which is particularly important in some cases. So English negation detection is a rule-based search for negative triggers like the patient had no muscle pain, he showed no signs of stress, the patient was unable to walk, patient denies chest pain, pneumonia is unlikely, and patient is not delirious. In other languages, we may instead need to use regular expressions to detect negation patterns. Now, the reason negation detection is important to use is because if you're searching for occurrences of muscle pain, you don't want to capture the times it didn't happen. Also, there may be some domain-specific negation you want to add, like a medical test was benign or negative, or claims notes that say injuries 0, witnesses none. So the next thing we're going to talk about is syntax, which is the sentence structure. It's basically how words are put together and their relationships with each other. So the first thing we can use to model a sentence structure is constituency parsing. This is based on current linguistic theory about how humans produce sentences. So let's look at an example of this. So in constituency parsing, we have hierarchically structured phrases or constituents. In other words, the parts that make up a sentence. Now, our sentence here is made up of a noun phrase, the patient, and a verb phrase, is experiencing persistent muscle pain. And this noun phrase and verb phrase are then further broken down into smaller parts or constituents. When we use language, we can start from a simpler structure like children sleep, and we can add descriptors to make longer phrases, like John's children are sleeping peacefully. We can also apply rules recursively to make sentences longer. For example, John's children, who were jumping on the trampoline earlier, are sleeping peacefully. So a constituency parsing's graphical representation is a hierarchical tree structure for phrases within phrases. Now, there's one downside to all this organization. It works best on well-formed sentences, but may not be accurate for diverse customer responses with incomplete thoughts or run-on sentences and so on. Now, there's a simplified version of constituency parsing called chunking. Chunking is faster and easier to use because sometimes all we need is the smaller phrases and not the hierarchical structure. And in grammatically incorrect sentences, the normal hierarchical structure can be broken, but in that case, these basic low-level chunks will still remain. To illustrate how important syntactic relationships are, Let's look at the following examples. I would like to see a bigger hospital in town, and they need a bigger hospital x-ray machine. So bigger hospital here is the same sequence, but it doesn't have the same meaning as the second sentence, where the bigger hospital is a modifier for the x-ray machine, which is the object of that sentence. Now, there is a specific problem that chunking and constituency parsing can't solve very well. Sometimes you'll have words that are different distances apart, but they have the same meaning. So when I show you a sentence like this, we can understand that blurred vision is the object of developed. However, these two closely related parts of the sentence may have other parts in between. And in this case, it's difficult to use constituency parsing to follow the tree down and capture these relationships in the text queries. We may need another type of parsing that captures meaning by helping us find objects of verbs, what noun an adjective is referring to, and so on. Which brings us to dependency parsing. And this is an alternative linguistic theory of syntax, and it's used to resolve just those sorts of problems. It provides another view of sentence structure that we can use to find these sorts of relationships. So syntactic analysis is one of many features that makes PolyAnalyst unique. These syntax relationships are drawn out by machine learning algorithms in the system, so we can then target specific relationships when we develop our text queries. And this gets us much more accurate results than out-of-the-box systems. But what makes PolyAnalyst especially unique is its ability to apply any or all of these methods to let the user target very specific linguistic structures and conceptual patterns. Most of these things are prepared automatically in the background when the text is indexed, and you can use them without being too concerned about how they work. And when you're able to combine your professional expertise with an understanding of language, meaning, form, and structure, you multiply your information extraction power. And by using all of these linguistic areas, we can extract a remarkable amount of meaning from these millions of characters that computers read as ones and zeros. Now, we'll quickly review how computational linguistics concepts are incorporated into advanced text analytics. So, as a review, let's say we're looking through text data like this to find possible side effects of our drug. And we've already cleaned up the data to correct misspellings, expand any abbreviations, and so on. Now, a simple keyword search for different side effects won't be very accurate. So we're going to need PolyAnalyst's linguistic analysis tools to help us solve the problem. So first, PolyAnalyst does lexical tasks like sentence splitting, tokenization, part of speech tagging, and lemmatizing the data by identifying underlying dictionary forms of all the words that appear in the dataset. We also index the text so we can search through it quickly. We then identify the concepts we're looking for in the records based on semantic dictionaries or word classes. And with dependency parsing, we know that someone was given the drug and the same person then experienced a possible side effect. And this is the query we would use for this type of task. So, by understanding how language works and its underlying concepts, we can target our queries like this, which gives us the power to get the specific information we need out of our data. And furthermore, this method is completely customizable and easily adaptable to new data sets or objectives. So that wraps up our introduction to computational linguistics. For the next topic, we'll be covering the use of advanced PDL operators so that you can construct more sophisticated queries.